Okay, last class we discussed about SPI interface. Now we are going to start the next interface called the SSP interface. Okay, so the SSP interfaces, because there are two such interfaces. You can see SSP0 and SSP1. SSP0 and SPI, they are shown as a single block. The reason I mentioned in the previous class, because both of them are sharing same interrupt line. So when you get an interrupt, you will have to check whether it is coming from SPI or SSP0 because they are sharing the same channel. That's the reason why they are shown together, but you can use SPI and SSP0 concurrently. Okay. It's not like it is a single block. Now SSP1 is here. Both are sitting on our APB bus. Now, unlike SPI, SSP is not a protocol as such. So you will see this is a flexible module which can support multiple protocols. So which all protocols are supported? It supports three protocols. One is of course SPI, which we have seen before. It's written Motorola SPI because it was introduced by them. Then another standard which is very similar to SPI called four-wire Texas Instruments SSI interface. SSI stands for synchronous serial interface. And again, another interface which again uses four-wire called the National Semiconductors Microwire buses. Okay, so SPI was there, then Texas Instruments and National Semiconductors. These are two other companies, I guess you know. They slightly modified it for their own purpose. So that made two more standards. One is called the SSI, Texas Instruments Synchronous Serial Interface. Other one is called Microwire. The interesting thing is all of them are using four wires. Yeah, so SPI, I mentioned, if you have a single slave, you can manage with four wires. If you have more than one slave, you will need 3 plus n. Okay. Three are shared and one slave select for each slave. Now, otherwise, yeah, all of them are synchronous serial communication, all three protocols. And each block, you can configure it either as master or slave. So most of the things are exactly same as whatever we have seen for SPI. Yeah, here there is a difference. 8-frame FIFOs for both transmit and receive. So if you remember in case of SPI, once you send a data, once you write to that data register, you cannot write a new data until that data gets sent out. Okay, because there is a single register where the data for transmission is kept. But here that is not the case. Here they are using a FIFO for storing the data, and that FIFO can store up to 8 frames. So one frame, yeah, in terms of SPI, one frame is like when you make slave select low, and when you make slave select high, that is like one frame. He can store like 8 such frames of data. Okay, so some kind of buffering is there, which might improve the performance. That is one difference. Another difference is for SPI, anyone remembers what is the frame size supported? How much data you can transfer per frame? Anyone remembers? No. Okay, so it was, yeah, 8 to 16. Yeah, minimum is 8, but it can go up to 16. Here it is 4 to 16. Yeah, so a little bit more flexibility is there. You can have as small as 4 also. Now this supports DMA. So details about DMA when we look at GDMA, DMA controller, we will discuss then. Okay, but it supports DMA. That means you can transfer directly from memory to this peripheral without the involvement of the processor. I guess you have seen DMA before. Anyway, okay, so this is the pictorial representation. So you can see still our MOSI, MISO, serial clock, and slave select, they are there. So when we are using SSP interface as SPI interface, when we follow SPI protocol, these 4 lines will be called like MOSI, MISO, serial clock, and slave select, which we have already seen. If we are using this interface for TI SSI, synchronous serial interface, same wires, but we are going to call them with different name. We will call it data transmit, DX, data receive, DR. Then this is clock. This is frame select, FS. Now, if you are using microwire protocol, this is SO, serial out, SI, serial in, SK, like serial clock, CS, like chip select. Okay? So it's like same wires, they have like three kind of incarnation, right? Kind of Trinity kind of thing. So physically, it is a same interface, SSP interface, but you can configure it for any of these protocols. This much is okay? Okay. Now let's look at the detail. Okay, so this you have already seen SPI protocol, so I won't be spending time on it. It will be exactly same as the SPI protocol that we mentioned in the previous class. Okay, so here also you can have multiple polarity for the clock. You can also have multiple phases. So that is what is shown here. One is phase 0, one is phase 1. Which polarity is this for the clock? Can you tell me? Polarity 0 or polarity 1?
1, sir.
Is it 1? Was it 1?
0, sir.
No, if it is not 1, 0. So guys, please make sure you go through the previous classes, okay? Otherwise, yeah, we'll be in trouble. Okay, so SPI, exactly whatever we discussed. Only difference is that time here there will be minimum 8 and can go up to 16. Here it can be up to like minimum can be like 4 also. That's the only difference. Otherwise, everything exactly same. This is how SSI protocol look like, synchronous serial interface protocol. So some difference is there. Here, serial select, slave select, it will remain low as long as there is a communication between master and slave. Here, it is slightly different. So what happens is, before the communication starts, the master will make this signal high. It will pulse it for 1 clock. After that, it will be kept low. So from the subsequent clock onwards, there will be data transfer. That's what you are seeing here. Okay. Now, here there is no concept of different clock polarity or phases. The master, he will be sending data always on the positive edge. You can see here, right? Master is placing it on positive edge. So where the slave might be sampling the data. What do you think?
Next
On which
positive edge, sir.
is it next positive edge? So he placed it here. If the slave samples it here, yeah, he may get it, but I mentioned, right, it is better to keep the sampling point like at the middle of the data so that all setup time, hold time, everything is satisfied,
Yes,
right? So maybe it's better to sample here on the negative edge. Okay, so this is one case where a single data, single frame transmission happens. Okay, so before the transmission happens, the master and slave, they should agree or you should configure them for the same transmission size. Otherwise, what is the problem? How will you decide? Don't look at this figure. Look at this one. How will you decide like where the data transmission is getting completed? Is there any indication here? Here it was the slave select will become high when the frame is over. Here, can you see anything in this figure? Can you see any indication like transmission is over from master? Yes or no?
no, sir.
So how the slave will know like, okay, master has finished transmission. What do you think? How the
So
slave?
maximum frame size.
It can go from 4 to 16. It is flexible actually. Yeah. It's not always 4, not always 16. So what might be happening? So there will be some register in the master as well as the slave. Through software, you should configure the same size in both. Okay? Both parties, they should know the transmission size, frame size. Otherwise, yeah, here there is no way. Another thing here, if you see, you can have back-to-back frame transmission. So see what happens. For the first frame, this will pulse, but when it is pulsing, there is no valid data. Valid data will start from the next clock. And if he is like transmitting back-to-back, along with the last bit, he will pulse it again. So here you can see there is a valid data. Then the next frame starts from the next clock. So here also slave should know what is the frame size. Otherwise this won't work. Okay, because if he doesn't know the frame size, he won't know like whether this pulsing is whether there is valid data along with this pulse, or this is like just a start of a new frame. He won't know unless he knows like each frame is 4-bit. If he knows like each frame is 4-bit, yeah, he will start counting from here 1, 2, 3, 4, and so this is valid. Along with that, it pulsed. That means from next clock there is a valid data. That's how he interprets. Is this okay? So this is similar to setting your port rate, right? UART, you know about UART interface? You have studied undergrad?
No, sir. Just the
UART you
name.
haven't studied? Oh,
We just know the name and function.
RS-232 you haven't covered. Okay, okay. Okay, then there is no point. Those who have heard about it, there is something called a baud rate. So we need to set the same baud rate in the transmitter and receiver so that they work properly. Similarly, here you need to set the same frame size in the master as well as slave so that the slave understands where the frame is ending. Otherwise, he won't know. Unlike SPI, we have the slave select to indicate where it is starting, where it is ending. Now, microwire protocol, this is from a different company, National Semiconductors, as I mentioned. So here again, you have this guy, CS, and you can see it remains low whenever the communication is happening or whenever the frame is valid. The difference here is in microwire protocol, the master, he will always send an 8-bit so-called control word to the slave. So it could be like a control word saying like, send me data from this particular register. Okay, it depends upon what kind of sensor you are interfacing. So if I have a temperature sensor, first the master will send a command, some bit pattern, which corresponds to send me temperature data, or send me pressure data, or reset temperature data. So first he will send a command for sure. That will be always 8-bit. That is fixed. Okay. And here also, master is placing it on the rising edge. So you can see like there is some slight delay from the edge. Now, what the slave does, once he receives this control word, he will respond to that. For example, if it is a command for reading the temperature, and if it is a temperature sensor, he will respond with the temperature data or a voltage corresponding to the temperature data, whatever the sensor is doing. Now that response, that size is not fixed. It can be anywhere between 4 to 16 bits. But the master should know it. Okay, so in the master, again, we will see there will be some register where we will configure like what will be the size of this response so that he can keep this chip select. This is controlled by master for that much duration. After that, the master will make it high, saying like not enough, chip is not selected. Is this also okay? So basically, it's the same thing, but the companies, they have improvised it for their own purpose. And our SSP interface in LPC, he can support all three with the same hardware. So now let's see how we can use the SSP, okay? How to configure it for different interfaces and all, different protocols. First of all, we have this control register. So in the control register, you have 4 bits here where you will set the transfer size. You remember what was the range of frame size? Just mentioned, right?
4 to 16. In SSP, 4 to 8.
Only one guy is there in the class. Come on, guys. Let me ask someone. Swapnil, are you there online? Swapnil Srivastava. Anshul, you are the quiz champion. Swapnil is here. Unmute. Mic is not working. Oh, great. Anshul, are you there?
Yes, sir.
Tell me. Oh, first I think I am hearing your sound. What was the range for the frame size?
4 to 8, sir.
What's it? 4 to 8. Was it 4 to 8? Huh?
4 to 16.
If it was 8, you don't need 4 bits here. It would be like 3 bits only. Okay, so you set the frame size here. This is what I said. If he is acting as a master, he should configure it. If he is acting as a slave, then also you should configure it. Okay. So SSP interface, you can configure it as master as well as slave, one of them at a time, of course. So in both cases, you need to configure what is the transfer size. So minimum is 4. So what happens is, like our Freescale register, whatever value you write here, that plus 1, that is the frame size. So you should not write 0 to 2 here, because 1, 0 to 3 is invalid transfer size. So if you write 3 here, transfer size will be 4. So for transfer size per frame is this plus 1. So if you want 16, what you should write?
1 1 1 1.
1 1 1 1. Okay, that is 15 plus 1. Do you remember in SPI what we used to write for that maximum size, transfer size?
100.
0 0 0 0.
Oh, good. You write all zeros, that is indicating 16. Okay. If you are using SPI here, that is not the case. You write 1 1 1 1. He will take 1 1 1 1 plus 1, 16. Fine. Okay, so this is a flexible module. So you need to say like which protocol he should follow because the timings are different. You have seen that is done here in the frame format. So if you write 0 0 SPI 0 1 PI 1 0 microwire 1 1 not supported. Maybe saved for future. Let me ask you a question now. How many SPI interface can LPC 2378 can have? Maximum number of SPI interfaces.
3.
Oh, okay, good. How did you find 3? Can you tell me the 3 ones? Which are the 3?
SPI is as usual 1.
SPI 0 and 1 is there. Okay.
SSP and another SSP 1 is there.
SPI is the 1, then SSP 0 and 1 are there.
SSP 1.
Yeah, so these both of them, that's why I want you to get it clearly, although it is shown as a single block. You can have this SPI running separately and you can configure this SSP also into SPI. You can configure this SSP also into SPI. So you can have up to 3. Yeah. Okay, this you already know, polarity and phase. So that is applicable only when you are configuring it for SPI. So only if you put 0 0 here, these two fields make sense. Otherwise, they don't have any significance. Okay, so for SSI and microwire, data is always placed on the positive edge of the clock. There is no concept of phase and polarity there explicitly. Now this one, serial clock rate, okay, as usual, this is a kind of Freescale register, but here you have 2 Freescale registers, okay. Second one we will see. So the effective frequency at which the interface will be running will be PCLK divided by whatever you write here plus 1, like our usual Freescale, that multiplied with one more register we will see, clock divide register. So they are providing 2 such registers. Okay. Because these interfaces, they are like generally very slow running. That's why maybe they provided, I don't know. That is an engineering decision they have made. Otherwise, they could have provided a single 16-bit register, so could have been done. But this is how they have done. You have this register as part of control register. So whatever value you write, that plus 1 will be used for scaling along with clock divide register, which we'll see soon. Now there is control register. Okay, so this bit, if you set it to 0, it will be in normal operation. If you set it to 1, it will go into loop back mode. What is loop back mode? Have you heard it in Ethernet or anywhere? What is loop back? If I enable loop back here, what will happen? Suppose I enable loop back in the master. Can you tell me what is going to happen? What happens when you enable loop back? Have you heard loop back before? Hmm? If no, tell me no. What is that?
No, sir. We
You
have
have never heard the term loop back. Okay. But what do you think from the name itself? It is there, right?
The data is again sent back to master.
Yeah. So from if you're using loopback on master, what happens is, yeah, your output will get connected to the input itself. That is not happening outside the chip. Of course, you cannot do it outside the chip, right? Sorry. So what happens is within the chip itself, there will be a connection like this. So whatever data he is transmitting, he will get the same data back. That is what is happening in loopback. Do you know any scenario where we can use this loopback? What do you think? Any application? No? Loopback is very useful while you are testing. You are sending some data. You want to check whether the data whatever you are sending is actually going out. So if you enable loopback, you send some data, you will get the same data back. Then you can compare them and check whether it is working or not. Does that make sense? Okay, so that is where we can use loopback. So yeah, so usually used during testing or to detect some error condition. Normal operation, that's why it's written like normal operation. So normal operation, we will keep this bit 0. Okay, so SSPE, that is used for enabling SSP. Okay, so you will have control in PCON-P register. Along with that, you can enable or disable each SSP interface by setting or clearing this bit. SPI also, there was a control. I hope you remember. You can either enable, disable in PCON-P, and in addition to that, you can enable, disable here also. ADC also, it was the power control. Master slave mode, yeah. So as I mentioned, each of them, they can act either as master or as slave. So whether it should act as master or whether it should act as slave is decided by setting this bit. So if you set it to 0, which is the default value, the interface will act as a master. If you set it to 1, it will act as a slave. It's straightforward. Slave output disabled. Okay, so this bit makes sense only when you are configuring LPC as a slave device. So if you configure LPC as a slave device, and if you don't want slave to send any data to master, okay, so he will be getting data from the master that he will accept, but you don't want to send back any data to the master, okay. In that case, you can set this bit to 1. If you make this bit to 1, for example, if you are following SPI protocol in SSP, if you set this bit to 1, your MISO master and slave out, that will be like permanently 0. No data will be sent back to the master. Okay, so again, maybe not very useful. These two, yeah, are what we are mostly interested in. Now, clock prescale register. This is what I said. So in addition to that scaling in the control register, there is another register where you can have more prescaling. So that is why the equation is like this: PCLK divided by this SCR plus 1 times clock divide register. So that is this guy. So you cannot, again, can't write any value that you like. You can write only even numbers between 2 to 254. Similar thing we have seen in SPI also. Anyone remembers what was the condition for prescale? You cannot write any value. There was a minimum value. Then, yeah, there was a similar condition. Do you remember? Yeah, Harshit, do you remember?
No, sir, actually.
It was 8. The condition was, that's why it was told like the maximum bit rate is 1/8 of the peak clock, because the minimum value that you can write there is 8, and you can write only even numbers above 8. Okay, that was the condition for SPI. So again, please refer old lectures also. Then there is a data register. Okay, so although it is written a register, internally we have seen the first slide itself. He is actually implementing a FIFO. So there is a FIFO for transmission. There is a FIFO for reception. What was the depth of the FIFO? How many frames maximum?
16.
So that was
8, 8,
one
8.
frame size. Yeah. So depth
8,
is 8. Okay. Depth is 8. Width can be between like 4 to 16. So of course, this is hardware. At runtime, you cannot dynamically change it. So internally, it should be, of course, 16-bit. Okay, so it is a FIFO, but to the software, this is exposed like a register. That means you won't have 8 addresses for the FIFO. You will have only 1 address given to the software. So whenever you write to that, what happens is, yeah, if you know how FIFOs are implemented, there will be a pointer which points like at which location he should store next. That will automatically increment. Okay, so from software, you feel like you are writing to a register, but actually you are writing to a FIFO. For transmission, so you will write to this transmit FIFO. For reception, you will read from the receive FIFO. Again, interesting thing is, for software, only 1 address is exposed. This I mentioned when I did SPI also. Do you remember? There also we have a data register, but the same data register is used for transmission as well as reception. So if software is writing to this address, it is actually getting returned to this FIFO. If software is reading from this address, it is not actually reading from this FIFO. It is actually reading from this receive FIFO. Okay. So again, those who want to know how it is done and all, again, shameless self-promotion. You go to my that YouTube channel, it is there. Okay. If I can find the exact video, I will send you how we do this in hardware and how we trick the software. People like feeling like they are writing to a register and they feel like they are reading and writing from the same register, but actually they are doing it from different registers or FIFOs. Okay, so that is our data register. Then, as usual, we have status register. Okay, so again, status is important. So this first bit, it is basically saying transmit FIFO is empty. If this bit is 1, means this transmit FIFO is empty. If it is 0, means transmit FIFO not empty. Okay, why this is significant? Can someone tell me? As when you write your program for this one, why this bit is important? What decision you will make based on this bit?
So there is no prior data.
Yeah, like, yeah, I cannot find any significance to this one. Okay, okay, transmit FIFO is there. Okay, it is empty means, okay, there is no data in that one. It is not empty means there is some data in that. Okay, but what we really care is this one. Transmit FIFO not full, transmit FIFO full. What is this bit's significance? What decision you will make based on this bit? This is important. Because FIFO, usually when you are writing, what you are worried about is whether FIFO is full or not. So if it is full, what you should not do? If a FIFO is full, what you are not supposed to do? Tell me, if a FIFO is full, what are you not supposed to do?
We should not add anything.
We should not write to that FIFO because the FIFO is already full. If you try to write something to that FIFO, that will not get stored in the FIFO, right? Because that guy is full. So here, why it is significant? So before you transmit anything over SSP interface, you should check for this bit. So when will you write to that data register? When this bit is 1 or when this bit is 0?
1.
Oh, 1. Okay. So this logic seems some kind of negative kind of thing. Okay. If it is 1, it is saying like it is not full. That is the condition we need. Only if FIFO is not full, you will write. If you find FIFO is full, you will wait until it becomes not full. Then only you are supposed to write. Okay. Receive FIFO not empty, receive FIFO empty. What is the significance? What is it telling you? When you read the status register, you found like either 1 or 0. What decision you will make?
We have received something or not.
So if you find
So-
like if this bit is 0, what you will do?
That means
not-
that no.
Not 0,
we-
sorry. If you found like this bit is 1, what will you do?
We'll read from it.
Read from where? Read from?
Receive
Which?
from the
Huh?
from the 5.
You will read from the data register, which is effectively reading from the FIFO. Okay. If you find like this is empty, that means if this bit is 0, that means there is no point in reading from there. Okay, you should not read because FIFO is empty. There is nothing. If you read from an empty FIFO, what will come out of the FIFO is not defined. You will get something, but it will be some invalid thing. So this is important. This is important. This is important. This, yeah, not that important. Receive FIFO full. Receive FIFO not full. What is the significance or any significance?
So it's like same only. Received 5 for empty.
This is similar to your transmit FIFO empty. Yeah. Okay, so if you have written your code properly, if you are operating normally, this bit should never get set. Okay, there should never be a condition where FIFO is full. FIFO usually becomes full when data is coming, but you are not reading. That is why the FIFO is getting full. So if you are properly managing your receive FIFO, this condition will never happen. Yeah, so if the FIFO is full means receive FIFO, it is now full. If any more data comes, that will not get stored in that FIFO. So you need to urgently read, something like that you can see. Okay. So again, normal programming, these two are very interesting. So if you manage these two properly, okay, these two, they don't have much significance. BC, this bit will become set whenever your SSP controller is transmitting or receiving some data. If this bit is 0, means SSP is idle. Again, not much importance to us because we have a FIFO. Okay, if there were no FIFO, for example, in case of your SPI, you need to make sure like he is not sending or receiving. That means his register is empty before you attempt a new write operation. Okay, so here, okay, even if this guy is busy, if you still have space in the transmit FIFO, you can still write to that FIFO, no issue. So let me repeat, important guys are these two. Interrupt enable register. Here again, interrupt enable interrupt status, they have done in again a slightly complicated manner. So this is our interrupt enabled register. Only 4 bits are important. Others are all reserved, not used. So you can enable interrupt under 4 conditions. One is overrun. Again, we are hearing the term again and again. Overrun basically means you received a data, but before you read that data, new data came and it overwrote it. Under what condition it happens here? SPI, there was only a single register. So of course, like new data, it came and overwrote the data in that register. Here you have a FIFO with a depth of 8. So this condition will happen like 8 frames came and you didn't read any of them. And the 9th one came and it overwrote some previous data in the FIFO. Okay. That is where this overrun error happens. Is this fine? So if you want to get an interrupt when this overrun happens, you need to set this bit to 1. If you don't want to get an interrupt when this condition happens, you make this bit 0. This one receive timeout. Okay, that means some data came to the receive FIFO and you didn't read that data within a so-called timeout period. Again, what is this exact value of the timeout? You cannot configure. That is something pre-configured in the hardware, in the chip. So some data came, you are supposed to read it immediately. You didn't read it within that timeout period. In that case also, you can enable an interrupt if you wish. So you can set it to 1 if you want that interrupt. Otherwise, keep it 0. This one, again, okay, you can set an interrupt whenever your receive FIFO is half full. So your maximum capacity is 8. If you want to get an interrupt when 4 data, okay, gets into the receive FIFO, you can set this bit. Okay, so you'll get an interrupt as soon as FIFO has 4 data. Can you tell me like why it is interesting? Whenever, again, I don't know, you are taking your reconfig course, right? I don't know, have you used any hardware FIFO? Anywhere?
No, sir.
Okay. So getting FIFO half filled is an interesting event. Okay. So what happens is when your software runs, one thing that you can have is like a greedy thing. So as soon as one data comes to your FIFO, you will immediately read it. Then next data comes, you will immediately read it. Okay. So if you are in, say, interrupt mode, not porting mode, okay, whenever you get a new data, it is like you want to read it. Do we have such an interrupt here? No. So what you will have to do? Suppose you want to read immediately as soon as a data comes. What you will do? What approach you will take? You are like very greedy. So as soon as some data reaches the receive FIFO, you want to read it then itself. Okay. You don't want to like wait for more data. What will you do? How can you do it? There is no special interrupt for that. SPI, there was an interrupt. Whenever a data is received, you will get an interrupt. Because a single register is there for storing that data. Here there is a FIFO. So there is no interrupt as soon as a data is received, but still you want to do it. What you will do? If there is no interrupt, what is the other way? There's only one more way.
RNA to 1, and whenever we need to set RNA to 1, so that whenever
you are not setting it. This is status register. Hardware is setting it. So what you should do?
So whenever the RNA bit becomes 1, we need to read data from the data register.
So how will you implement it? There is no interrupt for doing it. So what you will be doing?
We need to constantly checking for the status register.
What is that called? This constant checking.
Polling.
Polling. Okay, you should be in polling mode, and you will be keep on reading this register. And whenever you see like FIFO is not empty, you can immediately read. Okay. The issue with this is, as you know, if your processor is in polling, he won't be doing any other useful work. He will be just looking at your SSP interface. He won't be doing anything. So of course we need interrupt. Now now what will you suggest? You have a FIFO of depth 8. Okay. Will you prefer an interrupt as soon as a data comes to the FIFO, or will you prefer an interrupt when half of the FIFO is empty? or half of the FIFO is full, however you look at it. Okay. Which one will you prefer and why? You have interrupt in this case, of course.
When FIFO is full.
FIFO is full or half full?
Like
Which one?
all. So in half full we have to keep polling.
No. Half full, there is an option. That's what I said. There is an option to get an interrupt when it is half full.
Achha,
Okay. If you have an interrupt only when the FIFO gets full, that's the dangerous thing. You get an interrupt when the FIFO is full, then your ISR should come and start reading, right? By that time, if a new data comes, yeah, you will miss some data. Okay, so that's why they didn't keep like you get an interrupt when the FIFO is full. You'll get an interrupt when the FIFO is half full. Okay, now why getting interrupt when the FIFO is half full is better than getting an interrupt as soon as the FIFO gets their data. Or whenever FIFO gets their data, it can get an interrupt. Why getting interrupt when it is half full is better?
So as you said now that if it is full and while we are reading another data.
Full case, forget about full case. I'm asking half full and whenever the FIFO gets their data.
Then half full only, sir. Whenever
why?
it gets the data, because in that polling is there and processor is not doing any useful work.
Here there is no polling there.
Sir, in like
I'm
whenever
asking this, if you are designing a hardware, okay, you have the option to raise an interrupt whenever you get a data. You have the option to raise an interrupt whenever your FIFO becomes half. Which one will you choose and why? This is significant when you are designing your own hardware. Okay. Here they have already chosen. They will give an interrupt only when the FIFO is half full. Why getting an interrupt only when the FIFO half full is better than getting an interrupt whenever he gets their data? So remember, if you are not implementing this half full thing, you would have got 4 interrupts by the time the FIFO becomes half full. Okay. So why this one interrupt when the FIFO becomes half full is better than 4 interrupts when you get 4 data? Think.
Sir, in multiprocessor system, so
Not multiprocessor, uniprocessor.
No, sir, I'm telling multiprocessors. I mean, like more number of processors. Instead of having interrupt for every bit when it is received on FIFO, it is better to have 4, and after that there is a 1 interrupt for a half full.
Why it is better?
So that it will not stop other tasks. Whenever there is an interrupt.
You said multi-process. What did you use the word first? Multi-processor or multi-process?
Processes. Yes, sir. Process. Multi-process. More number of processes.
Multi-processor means you have many processes in the system. Multi-process, yeah, you have more than one process. Yeah, okay. Yeah. In some sense, yes. So remember what happens whenever an interrupt comes. Whenever an interrupt comes, you will go to the interrupt service routine, right? That's what is going to happen. So there will be a preemption and you are context switching everything. You will go to the interrupt service routine and you will do something. So if you are getting an interrupt for every data, what you will have, whenever you get an interrupt, you will go to the interrupt service routine. What you are doing, you will simply copy that single data from this FIFO to somewhere in the main memory, somewhere in the RAM, right? That's what you are doing, right? So in this case, is there any advantage of having this FIFO? There is no point in having the FIFO. As soon as you get a data, you are copying it. Then why do you need a FIFO? So FIFO is for buffering purpose. Yeah. So if you get 4 data, you get an interrupt. Then you go to the interrupt service routine only once. There you will copy all these 4 into the memory. And you are done and you will come back. Now, what is the logic in choosing like half of the FIFO? I'm spending too much time, I know, but yeah, I need to get something from you. What will be the logic? Make an interrupt. I'm saying it because some of you will become hardware design engineers. Okay, that's why. So there also you will be doing something like this. So why will you choose like you give an interrupt when the FIFO becomes half full? Why is it not like 90% full or something? Anyone? Just common sense, I just mentioned before.
So, but that thing can work in 90% also. Data loss.
Yeah. So this
I-
is based because when you get an interrupt, you are going to your ISR, there you are reading data, right? At that time also there is data coming on the bus, which will get stored into the FIFO. Okay. So we are setting it half the threshold based on the assumption that the time for starting your ISR and reading data from the FIFO will not take more time compared to putting 4 more data into the FIFO. Based on that faith, you set it to the half. Okay, in that good faith, you are setting it into the half. So I will suggest again reconfigure. You are using Vivado there, right? Are you using Vivado?
Yes, sir. Yes, sir.
Have you used any IPs in Vivado? IP-based design.
So we are going to use now. Like we haven't, but we have
When
got.
you use it, there is FIFOs. Okay, choose FIFO hardware implementation, and you will see the options. So your normal empty full everything will be there. Then you will have an option like programmable full and programmable empty. I'm saying like in Xilinx Vivado. Okay. So there you can specify at what value this programmable full should become high. So if I have a FIFO of 8, I can set any value from 1 to 7 as programmable full. So if I set 4 here, when the FIFO has 4 data, that programmable full will become high. And I know like half of the FIFO is full. Again, very important when we are doing packet processing everywhere, we'll be putting FIFO for buffering data. You don't want to go for an overkill or underkill. So when the FIFO or buffer is half full, you will start processing it. Okay, assuming your processing speed is good enough so that the FIFO won't overflow. But if you start processing much earlier, yeah, you won't be doing anything else, but just keep on checking this FIFO. Okay, anyway, I just mentioned everything. Okay, so this one, like receive half, you have transmit half option also. So if you set this bit, when the transmit FIFO is half empty, this case it was half full. In case of transmit, when it is half empty, you will get an interrupt. So this is used for enabling interrupt. Then, like your vectored interrupt controller, you can mask also. Okay. So assume you enabled all of them, but if you mask all of them, you won't get any interrupt. Okay. So in the datasheet also, you will see the meaning of mask is opposite of the meaning of the mask that we have been using till now. As per ARM, so this SSP module also NXP they bought from ARM. ARM makes a lot of soft IPs. So there they will say only if you mask you will get interrupt. So don't get confused. Okay. So the meaning of mask is opposite in this scenario. That's why, okay. Don't get confused. I just wanted to say.
So it's not same as VIC, right?
No.
In VIC masking is different. Like
in our GPIO, if you mask something, you won't get it, right?
Yes.
Here it is the opposite. So this one, I wrote it interrupt enable register. So the actual name of the register is interrupt mask enable register. Okay. So if you set it to 1, we will say it is masked, and only if it is masked, you will get interrupt. So that's why I simply dropped this one and simply called it interrupt enabled register. If you set it 1, interrupt is enabled. If you set it to 0, interrupt is disabled. That is easier to remember, right? Less confusing. So, okay, raw interrupt. So it doesn't matter whether it is masked or not. If an interrupt happens, the corresponding bit here will set. Okay, but if it is, let me say again, masked. If it is not masked, interrupt won't be raised, but the bit will get set. So same thing we have seen in VIC, right? Do you remember raw interrupt status? It was there also. So only if you enable, okay, so of course you have to enable it if you want to go to an ISR, but even if you haven't enabled it, the corresponding bit in the raw interrupt bit will set. Do you remember this when we discussed?
Yes, sir. Yes, sir.
Same concept. So here also same provisions are there, but this is not VIC. Within SSP itself, this provision is there. So raw interrupt means even if it is not enabled, okay, I don't want to confuse you. This mask, without using that term, it is difficult to say. Okay. If that interrupt happens, the corresponding bit will set here, but the actual interrupt won't be raised. For the actual interrupt to get raised, the corresponding bit should be 1 here. Now, okay, masked. Okay, again, let's forget about this mask and let's call it interrupt status register. So what will be here? Here the bit will set only if the corresponding bit is 1 here. So if this is 1, and if this condition happens, this bit will get set. If this is 0, and if this condition happens, it will get set here in the raw interrupt status, but it won't get set here. Is that clear? Because this term masking is slightly confusing. You can think of it as interrupt enabled register, raw interrupt status register, and interrupt status register. So if you want the bits in interrupt status register to get set, the corresponding bit should be set to 1 here. If it is not set to 1, it won't become 1 here. But if any of these conditions happen, irrespective of this bit status, the corresponding bits in the raw interrupt status register will become 1. Is this okay? Again, we'll be clear when we write some code. Okay. Okay, so why it is and all, again, okay, I don't want to go to that discussion. If you understood what is its significance in VIC, that is the significance here also. Because sometimes we don't want the interrupt to raise because we are in some kind of ISR. But once we are out of ISR, we want to check whether that condition happened. So in that case, I can go to the raw and check whether while I was in ISR, whether any new interrupt condition happened, and I can find it out. Okay, that's the reason. Because from SSP, there are no separate interrupt lines. Remember, from none of these peripherals, we have separate interrupt lines from here to vector interrupt controller. From one peripheral, there is only one channel, but interrupt can be raised due to multiple reasons. Okay, so while I am processing one interrupt, I don't want to get another interrupt from the same peripheral. So we usually disable it for that time. After that, we will re-enable it. But it is possible while I was running the interrupt service routine, same peripheral had an issue or it raised an interrupt, but it was masked. So after ISR, I can read this raw status and I can find it out. Okay, and interrupt clear. So these two interrupt conditions, if these bits are set, if you want to clear, you have to write 1 to these corresponding. So here it is write clear, but you are not writing to the status register itself. There is a separate register called interrupt clear register to clear it. So if you write here or here, this bit will clear or run. If you write here, timeout will clear. If FIFO half full, FIFO half empty, if you want to clear them, what you should do? Again, common sense. Here you got an interrupt saying like FIFO is half full. How can you clear it? You got an interrupt because FIFO is half full. How can you clear it?
Read from the FIFO.
You read from the FIFO, okay, and make it like less than half. You are done. That interrupt will go away. Here, transmit FIFO half empty. What you'll do?
We need to wait before it is less.
This is transmit. This is transmit. This is transmit. You can only write to that FIFO. Okay, so whatever you write it, it will get transmitted. So he's saying like it is still half empty. So he's saying like it is bad. Like this is half empty. So what he's expecting you to do? Receive, you said, right? Receive, he's saying like, okay, this is half full, read fast, otherwise it may overflow. Here he's saying like, yeah, your transmit FIFO is there, it is still half empty. So
Write it to.
Write more data, write more data. Okay. If you write more than half, that will go away. But it is possible like you don't have that much data, of course. In that case, you won't, right? Okay, so yeah, so it will remain there. But he will still transmit all the data. Okay. So that's why. Okay, so that's about our SSP. There is a DMA control register. You can enable DMA, but this we can discuss when we discuss the DMA control. So if you want to enable DMA on receive FIFO, you have to make this bit 1. If you want to enable DMA on transmit FIFO, this bit you have to make 1. DMA you have studied in undergrad, right? At least what it is?
Yes, sir.
Yes, sir.
Good. So our DMA controller is there. He can do DMA from memory to the transmit and receive FIFO without the processor reading from memory and writing to these FIFOs. If you want that to happen, you have to configure in the DMA controller, of course, that we'll do. In addition to that, we need to set these bits. Then only that transfer will be accepted. So that's about SSPOD. I took 1 hour.